Hey, good morning, everyone. Hope you had a good weekend.
Good morning.
Today, we're going to cover 6.2, and then your homework for that will be due tomorrow night at midnight. And then 6.3 we'll cover on Wednesday. I wanted to start out with any questions that you may have had on the homework assignments. I went ahead and brought up, I guess, the version of the homework that I have. Was there anyone that had a question on any of these problems? Want me to go through anything here?
I think number 8, I believe.
Yeah, I had one too. I think it was 11.
Okay, let me get
11 or 12.
is this the 8 that you're talking about?
I'm sorry, I think it's 7.
7. Is that it? Okay.
Yes.
Oh, yeah, sorry, I have to open up one more program before I can do this here. Come on. Where are you at? There you go. Okay. So let me look at this one. We're supposed to take a look at these two functions and determine what f of g of x is, and then also determine what g of f of x is. So find out what both of those compositions are, just switching the order, and then determine whether or not they're equal to one another. All right, so first thing I'm going to do here is let me do f of g of x. So to do that, what that means is I take the f function. Inside of the f function, I'm going to place the g function. So here's our g function right here. That's going to go in right there. So we're going to do the f function with g plugged in, 1/9 x plus 3. And then we're going to take that expression and plug that into the f function everywhere we see an x, but we only have an x right here in the f function. So into this f function goes, let's see, we put 9, and then now times x, but that's going to be times the expression that we just had there for g, and then we still have to subtract 3 from that. Is that clear? Any questions with that? All right. Okay, now I can just do multiplication. I can just multiply this 9 times the 9th, and that they cancel out. You just get a 1. And so it's 1 times the x plus 3. So you get x plus 3. You don't need the parentheses anymore. And then you subtract 3. And that just gives you x. So in other words, f of g of x is equal to x. So we're halfway done. Now we're going to do it the other way around. We're going to do g of f of x, which means we take the g function on the outside, and inside goes f. So that means we take G. Inside, we replace it with the blue, with the blue, which is the F function. So 9x minus 3. And then we take that and plug that into G for X. So everywhere we see the X in the G function, we will replace it with 9x minus 3. So let me go ahead and write down the G function, 1/9. And then comes the X, which is 9x minus 3, then plus 3. Like that. The 3's cancel. And all I get here is 1/9 times 9x. And again, the 1/9 and 9 cancel out, and you just get x. So g of f of x is also x. So these two are equal to one another. So they are equal. And we've determined that both of these turn out to be X. Does that clarify any issues you had there? Okay, good. Other questions? I heard, what did you say, 11 or?
Yeah, I think it was 11.
Let me see here. Just let me know when you get to, when I get to it.
Yeah, that one.
I thought I removed this question. Did I not remove this question?
No, you did not. I saw it
didn't.
last night.
Hold on a second. Let me go back through. I think I have to close this. Hold on. Weird. It may not have removed them. Let me see.
Yeah, I think all of the questions for the homework were there. None of them were removed
Let me see what this one
that I
is.
saw.
I think the last two were removed.
The last two. Okay, so you have.
Oh yeah, because it was a 13 problem homework, right? And we only had 11.
Yeah, okay.
Yeah.
All right, we can do the surface area one, which would be this one here. So 12 and 13, you don't have to worry about. This one here, I left this one here. So let's let's read through the surface area. S in square meters of a hot air balloon is given by this formula, where R is the radius of the balloon in meters. If the radius R is increasing with time, according to the formula, blah, 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 find the surface area of the balloon as a function of time. Okay, so this is actually something tied into something you would do in a calculus class. I just keep saying that, right? I'm like a broken record in here. All right, so I know this seems confusing at first, but just let me try and explain what's going on here. All right, so first of all, they're telling us that the surface area of a balloon, S of R, is a function 4 pi R squared. So the way to think about this is if you're given what R is, we can plug R into this function S, and it will spit out S of R, which is the surface area. So it's a function, right? The input is the radius of the balloon. The output is going to be your surface area, right? So in order to determine surface area with that formula, I need the radius. But they're telling me that the radius R is increasing with respect to time according to this formula, all right? Which is a separate formula. It says R of t equals 5/6 t squared, where t is greater than or equal to 0. So think about what this function does. It takes in t, time, and it spits out the radius, right? Time goes in, radius comes out. So this function R, right? That function R takes in t, spits out radius. What we're trying to do is find the surface area as a function of time. So what we want to be able to do is come up with some function that takes time in and spits out the surface area. How could we do that?
Is it the S of R times T?
So is it, what do you mean S of R times T?
Like, you know how we do G of F?
Okay, yes. Yes, okay, you said time, so we gotta be careful here because composition is not multiplication, it's composition, it's a different operation. So Alyssa's on the right track here. So think about it this way. We know how to get from radius to surface area, and we know how to get from time to radius. So if we put these together through composition, we could go from time over to radius and radius over to surface area, right? But that would require the composition of the functions. We would have to do something like S of R of T. In other words, we take the surface area and we plug into it the radius function. The radius function depends on T. Once we get that, we plug that in the surface area and we get the surface area. Can y'all see that? This is the composition, this chain right here, this chain of events right here, T to R, R to S is really just composition, just passing something through two functions. So let's do that. We're gonna do, first of all, the S function, and inside of it, we put the radius function, which is this, right? So 5/6 of T squared. Now that's now become the input. This goes into the S function for R. So when I plug that into the S function, I get 4 pi. And then whatever the radius is, which we just said was 5/6 T squared, but then we have to square that radius. So do y'all see in this last formula, this is 4 pi. Sorry, that was supposed to be squared, sorry. This is 4 pi R squared, but the R has been replaced with the function that we have for R, which depends on T. And now we just, we can just do some algebra here. Does anyone have a question on this? I would have to square this. When I square, I have to square both of these. So for the 5/6, I square the top and bottom, 25 over 36. And then the T squared, I square it, and that becomes T to the 4th because I multiply 2 times 2. And I think you can reduce this fraction. 4 goes into 4 once and 36 9 times. So you wind up getting like 25 over 9. That's the fraction that's left. I still have the pi, and then I have T to the 4th. This is your S of R of T. So now what we have is a new function, which now you give me T and I give you area, right? Questions? Okay, good. Anything else off this homework?
Number 4.
Number 4. This one right here? Does that look pretty similar to what you had? Was there one in particular you were having trouble with, or all of them?
I don't know. I just kept getting stuck on, like, I guess the first one, and so it wouldn't let me go through.
Yeah, so these can be a little tricky when you have all these fractions. So for part A, we're going to do f of g of x first, which means we take f and inside of it we plug in g. I'm going to stop using colors. Let's see how this goes. Okay, so f inside of f goes g. G of x is -1 over x. Okay, so all we've done there is just replace G with what it is. And now this right here has to get plugged into the F function everywhere we see an X. So this becomes, well, X first, right? Which is going to be the -1 over X. We're plugging that in over, and then bottom left corner is also whatever the G was, and then -4. That okay? Now, I think the computer should take that as an answer, but let's clean this up because as algebra students, we should be able to clean this up. What I'm going to do is in the denominator, I want you to notice that that 4 can be written as 4 over 1. And then what I'm going to do is get a common denominator between those two. So I'm going to multiply X here and X here. And that way I can put them together. So this becomes -1 over X over, okay, so I know that these both on the bottom will have the same denominator X. I put the numerator here, -1, together with this new numerator, 4X, but I have to subtract it, so -4X here. And then we have a fraction over a fraction, which is the same as multiplication of the reciprocal. So I can write -1 over X times, now I write this fraction but flipped over. So X over -1 minus 4X. And notice that the X's can cancel now. And so we will have, let's see, -1 over -1 minus 4X. That's a lot of negatives, right, in there? So maybe one more thing I could do is I could factor a -1 out of the bottom. And the reason I did that is because now these two negatives will become negative over negative is positive. So you get a final result of 1 over 1 plus 4X. Is that clear? Okay. In an effort to save time, I will try and come back to this one if we have time at the end of class, but I'll do one more of these. So you want me to do the F of F or the G of G?
I think that question had two parts to it. Like I think we had to put that in,
domain.
and then after you put that in, there was something else.
The domain, you're supposed to state
the
the
domain.
domain. Okay, yeah, sorry. I mean, okay, so let me finish this one up. The domain, what is the domain of this one? So think about what's happening here. X is going into G first, right? Comes out G of X, right? Goes into G first, then comes out over here as F of G of X. Right, so what I told you that you have to do here is you have to look at this final picture here, or the final result we got here. And you have to tell me what X can you not plug in. So when you look at this, we have a fraction, right? So the denominator, this denominator, 1 plus 4X, we need to make sure it's never 0, right? Because if that denominator is 0, we get division by 0, which is bad. So let me just move things around. I'll subtract 1 on both sides, and then I will divide both sides by 4. Okay, so I know right now X cannot be -1/4. If X is -1/4, the final composition is undefined. But there was one more thing you had to look at. Y'all remember? What is it?
Wouldn't it be the first function?
You have to look at that first piece of the composition, the G function, and you need to look at the domain of G. So what's the domain of this guy? What can you not plug in here for X?
0.
0, right? You cannot plug in 0 because you get -1 over 0, which is undefined. So along with this, you also have that X cannot be 0. And so if we think about this on a number line, here's 0, we cannot have 0, right? And we cannot have -1/4. But we can have anything over here anything in here over forever. So the way we'd write that in interval notation would be negative infinity to negative 1/4 parenthesis, because we don't want to include negative 1/4. Union, now continue negative 1/4 all the way till we get to 0. Again, don't include 0. And then from 0 to the right forever to infinity. So that's the interval notation of the domain. This is the domain of f of g. Does that help at all?
I think if I remember correctly, it was in set notation. They wanted it in set notation.
Set notation?
Yeah.
Okay, so you can
I'm
just,
pretty sure.
you could just put what it's not equal to then?
Yeah.
Yeah.
Yeah, I was about to say that.
Yeah.
I didn't test it on the computer, but or actually I did. For the thing, because like when I write it on my paper, like I just do like the x can't equal, and then I put commas and stuff. But you have to, for set notation, you have to put like each like one, so it's like the x can't equal 0, comma x can't equal.
Yeah, let's do it. Let's actually do it here. So here's my answer. Okay. All right, the domain is, okay, so the way that we read this is when you have this right here, x with a bar, what this means is we're saying, look, our answer are all the x's. Okay, so this right here just says, hey, it's all the x's. This bar means such that. Okay, so right now I'm telling you your answer can be any x, any value you want. But now I'm going to say such that, and I'm going to give you some restrictions. So I'm going to say here now that x can't be, what was it, negative 1/4, and x can't be 0. Okay, so it's any x you want except that x can't be negative 1/4 and can't be 0. Let me try and type this in. So it says, type in inequality, use integers, fractions for any numbers in the expression, use a comma to separate your answers. So I'm going to put here x cannot be 0, comma, x cannot be negative 1/4. Let's see if it takes it. There we go. That clear? Okay. So look, let's save this one. If there's more you want me to do from that at the end of class, I'll try and squeeze that in. Okay, let's get to today's material. Today's actually going to be, I think, a short day, but we've already taken 20 something minutes, so I don't know. Let's see how it goes. We're going to cover one-to-one functions and inverse functions. So the first thing we're going to do is talk about the definition of what it means to be a one-to-one function. So we already know that to be a function, we had to have one input goes to one output. But now we have a stronger condition, all right, a stronger condition. So we have some pictures here. A function is said to be one-to-one if any two different inputs in the domain correspond to two different outputs in the range. That is, if x1 and x2 are two different inputs, then it's one-to-one if f of x1 does not equal f of x2. Okay, what? All right, so let me just do it this way. When we were learning what a function was, I said if you had a number like, let's say 1, 2, and 3, that let's say 1 went over here to 2, let's say 2 went over here to 4, and let's say 3 went to 4. This would still be a function, right? This is a function. Yes, because to be a function, all you need is that for each of these inputs, it goes to one place. Doesn't matter where it goes, it just goes to one place. See, this would be the example where we don't have a function. What if you had this? Let's say this goes here, this goes here, this goes there, and that goes there. See, this would not be a function. Not be a function, right? It's not a function because right here, this point goes to two different places. And that's like when I was talking about like a car wash. That would be like a car wash where you put one car in and two cars come out. That's not a function. That doesn't work that way. What you can do to be a function is single input, single output. Okay, that's a function. But one-to-one means that for each input, it goes to exactly one output, all right? But it has to be different than any other output that the function spits out. So if I take any, look at this first example here that I put that was a function. Notice that 2 and 3 go to the same point. They both go to 4. Even though that is a function, this would fail to be one-to-one. Okay, so this is not one-to-one. I'm going to write 1-1 instead of one-to-one from here on out. It's not one-to-one because you had two different outputs, right? I mean, two different inputs. We could call this one x1 and x2, and they both came out to the same place. F of x1 was the same as f of x2. They were equal to each other. Not good, not one-to-one. So this diagram shows you kind of examples like I just did. This first one is one-to-one. One input goes to one output, but every single input goes to one distinct output. Nothing goes to the same place. Here's an example of a function, right? This is a function. Each input goes to one place, but these two share the same output, so it's not one-to-one. And on the last one, this one is just not even a function because this input goes to two different places. Does that make sense? Questions? So one-to-one is a very important concept, all right, for functions. It's a very strong condition if a function is one-to-one. And there's a very easy way to tell visually. So we should all be familiar, oops, yeah. We should all be familiar with the vertical line test. Remember, the vertical line test is what we use to check to see whether or not we have a function. The horizontal line test is what we check to see whether or not a function is one-to-one. So here's the test. Every horizontal line intersects the graph of the function f in at most one point. So we can never hit it more than once. So look at this parabola right here. Is this parabola a function? A function? Yes, I'm seeing thumbs up. And that's because it passes the vertical line test, right? If I draw vertical lines, I never hit more than once. But if I try and draw a horizontal line, I'm going to hit it more than once. So this is a function. I'm going to put f, yes, right? It's a function. But one-to-one, no, it's not, right? Where you look at this one, this is a function, right? Passes the vertical line test. So it is a function, but I don't know why I'm doing it. It is not. Oh yeah, come on. Let me clear that. So this one is a function, yes, and it is one-to-one, yes. This one was a function, yes, but one-to-one it was not, right? Very easy way to tell whether or not a function is one-to-one. Let me give you another example, all right? You tell me. Function, yes or no? Yes, okay. One-to-one? No, okay. Right, passes the vertical line test, fails the horizontal line test. Doesn't always fail. Like if I draw that horizontal line, I hit once. Draw that one, it hits once. But so far, so good. But there are places where I hit it more than once. And so it would not be one-to-one. Here's one. Try this one. Function, yes or no? Not a function, right? One-to-one? I'm seeing thumbs up for one-to-one. It is not one-to-one. I know that's confusing. Well, hold on, wait a minute, what happened? Let's look at the definition. Let me go back to this definition. Let's read this. A what is one-to-one? A what is one-to-one?
A function.
Function is one-to-one, right? We can only talk about one-to-one if we're looking at a function. If we're not looking at a function, one-to-one is out the window, okay? So you must have a function to talk about the one-to-one property. So this, I gave you this intentionally because it always tricks students. Look, this right here is not a function. As soon as it's not a function, you can't even start talking about one-to-one anymore. Does this pass the horizontal line test? Yes, but the horizontal line test only works if we're talking about a function. All right, so you got to be careful. Okay, we continue. So why is it so important for us to have this property of one-to-one? Like, what's so special about it? What makes it important to us? Well, we can define here what's called the inverse function. So we start off with this. Suppose that you have a function of x, right? Because I'm using that notation f of x, that tells you that you have a function. And suppose that it's one-to-one. Okay, so I've got some one-to-one function, passes both the vertical and horizontal line test. The correspondence from the range of f to the domain of f is called the inverse function of f. The symbol f with the little -1 up on the top right is used to denote the inverse function of f. In other words, if y equals f of x is a one-to-one function, then it has an inverse function. So all it's saying is this. If we have a function that goes from here to here, f, right? And it's one-to-one, that means that for every input, it goes to exactly one place, and there's never any 2 points in the domain, right? This domain of f, there's never any 2 points that go to the same place. Then that means there has to be a way to go backwards and go from these points back to where they came from. And notice that none of these points over here will ever go to 2 places, right? This will never go to 2 places because of the one-to-one property. Every input on the right side must go to exactly one place on the left side, because it's one-to-one, because f was one-to-one. So the domain of f, right, spits out over here the range of f. I use ran f to denote the range of f. So there's a correspondence that goes from the domain of f over to the range, right? That's the function f. It takes things from here, from left to right. If it's a one-to-one function, there must be some inverse function, which we denote with f with a -1, that will take you from the range of f back to the domain of f. So this actually would be called the domain of the inverse function, right? These are the inputs to the inverse. And then this would be the range of the inverse. So notice that the domain of f and range of f are equal, right? And the range of f and the domain of f are equal. That's terrible equal sign. These two are equal, right? These two are equal. But you have to have a one-to-one function to do that. So this is good. This is like, what this is telling us is that if we have a one-to-one function, there's a way to undo it. So it's like this, you know, the car wash I was talking about. You take your car, you put it in here, right? You put your dirty car in here, comes out over here clean. We could call that the f function. If that was a one-to-one function, that means there's some other thing that I could put the car in here and come out, and it'll come out with all the dirt exactly where it was. It'll put all the dirt right back on the car. Okay. So it'll whatever f does, the inverse function undoes it. But you have to have one-to-one in order for that to happen, for that to be possible. All right. Okay, questions? Here's another way of looking at the same picture. Okay. If your function f is 1-to-1, okay, then you can imagine this chain of events. You take some x, right? You plug it into the f function, it comes out f of x. Then you take that, you plug it into the inverse function, and where should the inverse function take this? What does the inverse function do? What would this turn out to be? If I start out here with x, I go through the car wash, it comes out clean car, and then I take that clean car, put it through the inverse function. What should it come out over here? What should this be equal to here at the end?
X.
This composition. It should be x, right? This should be x, right? That's what should happen, is that we have this property right here, that when you put the inverse function together with the function, I forgot the parenthesis, then it should undo everything and just spit out x. Okay, let's take a look at the graph of a one-to-one function. So this theorem says the graph of a one-to-one function f and the graph of its inverse function f inverse are symmetric with respect to the line y equals x. I showed y'all this already. I know I've talked about some of this last class. So look at this blue function. The blue function is the function f. Is the blue function a one-to-one function? Look, just the blue, right? Pass both the vertical and horizontal line test. Okay, so it must have an inverse, all right? So I want you to look at, let's just look at this yellow point for a second, all right? What's happening here, they give you the coordinates A3, B3. That means if we move to the right, here's A3, that's the X coordinate. The Y coordinate is B3. So try and visualize it this way. If A3 goes into the function f, what does it come out as? So A3 goes in, what does it spit out? B3, right? So where should the inverse function take B3?
A3.
Back to A3, right? So let's look at the inverse function, the one in red. If we look at this point right here, do you see that B3 goes in, A3 comes out? In other words, these 2 points, this one and this one, those 2 points, whatever the point is on F, the inverse function will just be that point, that ordered pair flipped over. That's all it is. All of these correspondents are just A2, B2 is now B2, A2 on the inverse. A1, B1 is now B1, A1 on the inverse. So every ordered pair just changes places. That means if I just give you the graph of F, right? If I were to have just given you the blue, you could have drawn the red one by just switching all the ordered pairs and then drawing the curve. When you're done, you should have a reflection over this diagonal line y equals x. Anyone remember what I called this y equals x? What that's called, y equals x? The identity. That's called the identity function, the diagonal line. When you draw f and its inverse together, they should be a symmetric or a reflection of themselves over the identity. I think we're going to have a chance to practice one here. Okay, why don't you take a few minutes, see if you can draw the inverse of this function. First, look at it. Is it a function? Is it one-to-one, the blue one? Vertical line test, horizontal line test, good. So it should have an inverse. Take a moment to see if you can draw it. Notice they give you exact points now, 2, 1, -1, 0, -2, 1. Draw the inverse. Let's take 2 minutes. All right, sorry about that delay. I had a phone call there right in the middle of that. Okay, so I'm gonna do it real quick. So the way I'm gonna do this, I'm going to just switch these. That's gonna become 1, 2. This other one's gonna become 0, -1, and this one's gonna become -1, -2. So I'm just gonna plot those points. 1, 2 goes to the right, 1 up 2. This one's 0, -1 just means move down 1. And then -1, -2 is to the left 1, down 2. So there are my 3 points that are on my inverse, which is pretty helpful. But what I'm going to do now is I'm going to get a straight edge and I'm going to draw the identity function. So the identity function is the function y equals x, which looks like this. When you plug in 1, you get 1. So that point's on the identity. When you plug in 2, you get 2. And when you plug in 0, you get 0. So it's that perfect 45-degree diagonal line that goes through here. And try and make it dashed. Okay, there's my dashed diagonal. And I need this to be a reflection of the red curve is going to be a reflection of the blue curve over that dotted line. So I'm going to have a straight line connecting here. And then a straight line connecting those two like this. Oh God, that's terrible. There we go. There's the inverse function. When we label it, this is f inverse of x. Questions? Y'all are okay? When's our next test? I feel like it's soon. I don't know why. Okay, end of the month. Okay, so we got time. All right, moving on. All right, so now, what if I give you 2 functions, okay? What if I give you 2 different functions and I ask you, are these inverses of one another? But I don't give you their pictures, okay? I don't give you the graphs. I just give you the algebraic functions and I ask you, hey, are these inverses of one another? Does this function undo this one, right? How do you do it? So this is called verifying an inverse function. To show f and f inverse are indeed inverses, we must show both of these are true. So we have to show this is true and this is true. I'm going to show you a picture of what this is saying. This first, let me do the second one here. Let me do this one first. What this one is saying is that x goes through f first, comes out as f of x, and then that goes through the inverse and comes out as x. In other words, x started out, went through f inverse, came out unchanged. We have to show that's true. The other one says that we have to also show that if you start with the x in the inverse first, then you plug that into the f function, that again, it will come out unchanged. So you have to go both directions. X goes into f, that f inverse comes out unchanged, and then you do it, x goes into f inverse, then through f, and then it comes out unchanged. You have to show both. So here's how we're going to do it. Here's an example. There's 2 problems here. We're going to do part A first. So I want to verify that these are inverses, okay? I want to verify that these are inverses of one another. So let me start with this. Let me do, I have to remember, I have to show 2 things. So the first thing I'm going to try and show is that f of f inverse of x is x. So here, because this is g, I'm going to use g instead. G of g inverse of x, right? What is it? Well, we take g, inside of it, we plug in the inverse. So this is composition. This is last section. That's all we're doing right here is just doing what we did last section. So we're going to take g, inside of it goes the inverse. The inverse is this. So I'm going to put in there the cube root of x. And now I'm going to plug that into this right here gets plugged into the G function for X, right? So this becomes the input of that function. And what does G do? It takes whatever you give it. I'm giving it cube root of X. It takes that and it cubes it. And what happens when you cube root? Sorry, what happens when you cube the cube root? They go away, right? And you just get X. Check. I've shown the first thing. I showed that when you plug X in to the inverse and then plug that into G, that you indeed get X. It has to be X at the end for these to be inverses. Halfway there. Now I need to show it works the other way around. If I do the inverse and plug G of X into it, what is that equal to? So I should do that here. So G inverse, I'm going to plug in the G function. The G function is X cubed, right? And then that gets plugged into the X into the inverse function. So I will now take the cube root of that, the cube root of X cubed. And this is like the reverse of this. I'm taking X cubed and I'm taking the cube root. Again, they kill each other off and you just get X, which is exactly what I needed to show. Do y'all see that? Composition both directions winds up being X. Therefore, we have verified that they are indeed inverse functions. Any questions? Let's do part B. Same thing, they give us two functions. I don't have room here. Move down here. I want to verify that these are inverses. So let me start. The first thing I'm going to try and show, first thing I'm going to do is I'm going to take F, and then inside of it, I'm going to put F inverse. This is very similar to the problem we started class with. So F is here. Inside of it goes the inverse function, 1/2 X minus 3. So that will get plugged into X, in for X on the original function F. So this is 2 times 1/2 X minus 3. Okay, I do 2 times that first, then plus 3. And this better turn out to be X. Hit the 2 and the half together, that goes away. You get X minus 3 plus 3. And of course, the 3's cancel, you just get X. Okay, do it the other way around. Do the inverse and then F inside of it. So this is the inverse function, but inside you're plugging 2X plus 3. And then now we take that input and plug it in right there for that X into the inverse function. So this becomes 1/2. And then the X we're plugging in is 2X plus 3 and then minus 3. This looks very familiar to the problem that Alyssa asked about earlier. The 3's go away, you get 1/2 of 2X, and that again becomes X. So check, both of them worked, they're inverses one another. So in other words, if you want to verify two functions are inverses, you're just really doing what we did last class. You're doing the composition, but both ways, F of G and G of F, basically. Okay, questions? We're good or no? All right. Okay, all right, we're moving on. Verify that these are inverses. Same question, harder functions. All right, you ready for this? These are more complicated functions. So what do you want me to let you try it first? Do y'all want to try this one on your own or no? You want me to just do it? What do y'all want?
Can you go through it?
Go through it? Okay. All right, so let me start this off. First thing I need to do is try and show that I'm going to go with F inverse. I'm going to do that one first. And I need this to be X. When it's all said and done, I need this to turn out to be x. Okay, so I'm going to take the f function. Inside of it, I'm putting the inverse. The inverse is this one. So 1 over x plus 1. That's what's getting plugged into f. So everywhere I see an x in the f function, I'm plugging in this 1 over x plus 1. Ugh, that's going to be ugly. Okay, here we go. So it's 1 over, right? And then x, which is 1 over x plus 1. I've replaced it with the yellow piece, but then minus 1. Everyone see the yellow piece right here is just this function getting plugged in right there. Actually, this ain't too bad. Look, the ones on the bottom cancel. Y'all see that? Plus 1, minus 1, gone. So all you're left with is 1 over x. And isn't 1 divided by a fraction just the reciprocal? Can't we just flip that over? And doesn't that become x over 1 or just x? Hey, good. That worked out nice. Halfway there. Now we got to do it the other way. Inverse function on the outside, f function on the inside. So I want to take the inverse of the f function, which is 1 over x minus 1. And this piece is going to get plugged in right there into the inverse. Here it comes. So the inverse is 1 over that green thing, 1 over x minus 1, and then plus 1. So there's the green piece, that thing getting plugged into this inverse function for that green piece. Again, this is actually not bad because I can just do the reciprocal again. 1 over a fraction, doesn't that first one just become x minus 1? Right, because 1 over the fraction flips it over, and then I still have plus 1. And the ones cancel, and I just get x. That seemed like it was going to be bad. It actually turned out to be not as bad as it looked. Do y'all agree? I mean, just a couple of flipping up things and canceling, and we're there. Okay. All right. Now, there are some, we didn't talk about domain here, but there are some values we can't plug into these functions, right? Like you can't plug in 0, right? Can't plug in 0, and you can't plug in 1, right? 1 would make this function mess up, 0 would make this function mess up. So when it asks here, for what values of x is this true, there are some limitations, right? You'd have to look at the domain of these compositions, which I didn't do, but well, let's see on what they're doing here on this right here. That's this one we did here. That's this one we did here. The only x we couldn't plug in would be 0, right? If we try and plug in 0 to this, it's going to be undefined. So the answer to this one would be, you know, everything except x cannot be 0. All right, now, what we just did, okay, what we just did is I gave you 2 functions, right? And I said, hey, show me that these are inverses. And we did, all right? But what would be better is if I gave you a function and I told you to go find the inverse, right? Like, okay, start out with this, now go find its inverse. So I only give you 1 function. So how do we do it? There's a set of steps, and these are the steps. I'm just going to state what the steps are first, and then we'll do an example and they'll make a little more sense. So if we're given a function f of x, now it has to be 1-to-1 for us to be able to do this. We can find the inverse, I should put here, if it has one. right? If it has one. As follows. So the first thing we're going to do is we're going to take our function, we're going to replace the f of x with y. Then we're going to switch all the x's and y's. Then we're going to solve for y, and then we're going to replace that with f inverse of x. Okay, what? All right, that's this weird. Let me just take these over here. I'm going to just put it right here. We're going to do this example. All right, so here we go. Find the inverse of the function f of x equals 2x plus 3. Can somebody, just by looking at this function right here, tell me whether or not it's 1-to-1 and why? Is 2x plus 3 a 1-to-1 function?
Yes, sir.
Why?
It's not a parabola. It isn't. It is a straight line.
It's a straight line, right? And if you draw me a straight line, as long as it's not vertical, right? As long as it's not vertical or horizontal, right? You draw me a line, as long as it's got some pitch to it, it's going to pass both the vertical and horizontal line test, right? As long as it's not straight up or straight, or, not flat or straight up. So we already know this is 1-to-1. We're being asked to find the inverse of it. So let's do step 1. Step 1 is to replace f of x with y. So I'm going to take f of x, replace it with y. Okay, that's step 1. Step 2, I'm going to switch the x's and y's. So what I mean by that is everywhere I see an x, I'm going to put a y. Everywhere I see a y, I'm going to put an x. Now, students always ask me, why are we doing that? Why do you do this next step where you switch the x's and y's? It has to do with the fact that, remember when I showed you that picture, I said that if we have a point on the graph of f, right? If we have a point on the graph of f, the inverse just switches the two, right? So if this is x and this is y, this becomes y and this becomes x. So they flip all the time. So that's why we're doing this technique. We are going to switch the x and y just like the inverse function needs to do. That's step 2. Step 3 is we are going to solve this equation for y. Okay, we're going to try and get this y by itself. So algebraically, I'm just going to subtract 3 from both sides. And then I'm going to divide both sides by 2. And now I have an equation for y. Step 4 is to replace the y with the f inverse notation. So x minus 3 over 2 equals f inverse of x. I'm going to write that a different way. I'm going to write it up here. F inverse of x equals x minus 3 over 2. I'm going to do one more thing. I'm going to write it this way: 1/2 x minus 3/2. All I did was I divided each of these by 2. Okay, so x divided by 2 is the same as half of x, and 3 divided by 2, of course, is 3/2. The reason I did that is because I think this is easier to know what it looks like when you graph it. This is also a line. And it wants us to graph both of these. Okay. Are there any questions up to this point? I'm going to graph these. I'm going to try my best, then we'll use a computer to graph it. Okay, let me do the blue function first. 2x plus 3 is a line. It has a y-intercept of 3, so I can go up 1, 2, 3. Here's 3. And the slope of this line is 2 over 1. So rise over run, go up 2 to the right 1. Put a dot. And then I could draw a straight line through those 2 points. Okay, this is F. Now I'm going to attempt to draw the inverse. Well, actually, I'm going to draw this one right here. The y-intercept of that one is -3/2 or -1.5. So I'm going to go down -1. Here's -2. So -1.5 is here. And my slope is a half. So up 1 to the right 2, up 1 to the right 2. Let me do it again, up 1 to the right 2. And I draw a line connecting those. And then if I wanted to, I could come in here and draw the identity, which would be the diagonal. And I hope you would be convinced that those look like their reflections are symmetric over that diagonal. What do you think? We okay with this? So if I give you a function, if it has an inverse, you're going to replace f of x with y. You're going to switch the x's and y's. You're going to solve for y, replace the y with f inverse of x. Let's try a harder one. Find the inverse of this function. All right, let's go through the steps. First step, I replace f of x with y. Okay, easy part. Second step, everywhere I see an x, I put a y. Everywhere I see a y, I put an x. The first two steps are the easy ones. The third step is the hardest. You have to solve for y. Please pay attention to this problem right here as I solve for y. I like to give problems like this on tests, all right? Because the algebra here is a little tricky. On the previous problem, how hard was it to solve for y? When we did step 2 and we were going to step 3 to solve for y, all we had to do is move the 3 over, right? Subtract 3 and divide by 2 and we were done. We had y by itself. Very simple to get the y by itself. Here in this problem, it's not going to be as easy because we have y's both in the numerator and denominator. Do y'all see that? So watch the way I do this. I'm in step 3 now. First thing I'm going to do is I'm going to clear the fractions or clear the fraction. There's only one fraction. So what I'm going to do is I'm going to multiply both sides of the equation by y minus 1. Now I do that because it will cancel out on the right. We won't have the fraction anymore on the right. So on the right, we'll just have 2y plus 1. That's all good. But on the left-hand side, we still have, well, we have y minus 1 times x. So I'm going to distribute the x through. Now I have x times y minus x. Now, careful, be very careful here. You might be thinking, oh, look, I almost have y by itself. I just need to move the 1 over and divide by 2, right? Move 1 over, divide by 2. Wrong, because you have a y on the other side as well. Do you see you still have y over here? You need y by itself. On the other side, you can't have any y's. That would be a circular sort of argument to have y on both sides. Let me write it down. I just want y'all to see this because this is a huge mistake people make. Okay, let's say I subtracted 1 on both sides and I got that. And then let's say I divided by 2. Okay, then I agree with you. I have an equation for y, right? But what do you need in order to know what y is? You need to know what you would need to know what x is, but you would also need to know what y is. So how could you possibly know what y is if you need to know what x and y is? Like you can't know y if you don't know y, right? So this does not work. We need all the y's on one side. Nothing else can have y's on the other side. So the way I'm going to do this is I'm going to bring everything that has a y to one side. I'm going to choose the left side. Everything that does not have a y to the other side. So all I did here was subtracted 2y on both sides, and I added x to both sides. Y'all follow that algebraically? Just moving things around. Why do you think I did that? What am I going to do now? What do both terms on the left-hand side have in them? What do both of these terms on the left have?
Will you factor out
Y.
A y, you can factor out a y, can't you? I can pull a y out, be left with x minus 2. On this side, x plus 1. And now, so that was like a greatest common factor, right? I pulled out the y. Now, how could I get that y by itself? I have multiplication times that thing in parentheses. So how can I undo that?
divide by y?
Divide by, not by y, we want to leave y there. Let's leave y there. So divide by what?
X minus 2.
X minus 2. We're going to divide by x minus 2 here, divide by x minus 2 here. They'll cancel. And you'll be left with y equals x plus 1 times x minus 2. Now we have solved for y. Step 4, replace y with f inverse. So f inverse of x equals x plus 1 over x plus 2. Sorry, x minus 2. Boom, got it. All right. Okay, what I'm going to do now is I'm going to show you the graph. We're going to graph both of these just to see if it looks like we got it right. 2x plus 1 over x minus 1. 2x plus 1. 2x plus 1 over x minus 1. I think I forgot already. Over x minus 1. Okay, that's the graph. This is the graph of the original function f, all right? Let me put y equals x here. That's the identity. Okay. By the way, look at this red graph. Is it 1-to-1? Does it pass the vertical and horizontal line test? It's hard to tell, but it does, right? It does pass. So it should have an inverse. Now I'm going to graph what we got as the inverse. We got x plus 1 over x minus 2. X plus 1 over x minus 2. Here it comes. There it is. Does that look like the purple one is a reflection of the red one? If you reflect it over the diagonal dotted line, just kind of tilt your head and look at it. They do look like reflections, don't they? You'll see, it's like we take this whole piece right here. Imagine just flipping it over, bringing it over here, and it would land right there. If we took this red piece right there and flip it over, it would land right here. So they are indeed mirror images of one another. Okay, questions? All right, let's see where we are here. All right, find the inverse of this function, f of x equals x squared, if x is greater than or equal to 0. So I want to show you something here. F of x equals x squared. Before we do this problem, I want to graph this for you. Here's x squared. This is a function, but it is not 1-to-1 because it fails the horizontal line test, right? It fails the horizontal line test. However, they're telling us x can only be bigger than or equal to 0, which means that the graph that they want us to look at is only there we go. There we go. So they want us to look at that parabola, but they only want us to look at the right side of it for only values of x greater than or equal to 0. So now if we're only looking at that, then that is a function passes vertical line test and 1-to-1 passes horizontal line test, right? So we should be able to find the inverse of it. There is an inverse, right? There's some function that should be a reflection over this diagonal line. So let's go find it. So first thing I'm going to do, first step, I replace f of x with y equals x squared. Step 2, I want to switch the x's and y's. I put x here, I put y squared there. And step 3, I want to solve for y. How would you get y by itself here?
You just square the y.
Square root, right? You take the square root, right? Now, when you come in and you take the square root, aren't you supposed to always do plus or minus? Anytime you take the square root, you should do plus or minus. So I'm going to do plus or minus the square root of x equals, now when I take the square root on the other side, you just get the y. But wait a minute, this is two different answers, right? This is two different answers. So let me graph both of those answers. One of the answers was square root of x, right? And the other answer was negative square root of x. Which of those is the correct answer, the red or the blue? Which one looks like a reflection?
The red.
The red. Okay, but how are we going to know that? How are we going to know that from this? How do we know, is it y equals root x or is it y equals negative root x, right? We don't know. Well, the key to knowing this is to know the restriction on what the y values have to, or I should say what the x values were, right? The x's have to be greater than or equal to 0, right? Yes. Which means you can only have positive answers, which means this can't happen. You can have negatives, right? That has a negative in front. So it has to be this one. So back here, we would not want this one. There it is. So the correct answer is f inverse of x equals the square root of x, right? And that is our inverse function. Okay. Oh, that's all I have today. That's it. So kind of a short section. I'm not gonna go any further. I'm not gonna start the next section. I don't think. Well, we can talk a little bit about something. I don't want to go too long. So I'll give you a choice. I have a couple of little things I want to talk to you all about, right? But does anyone have any questions on this or on what we started class with? Remember those problems that I had started looking at? Do you want me to go back and look at any of this? I'd done f of g and I didn't have time to do any of the others. Would you like me to do another one of these or?
These are going to be the same answers that are going to be in the homework solution videos, correct?
The same answers? Yeah.
Or
If
like
it was
the same, not the same problem. I guess like the same problems, but I guess like the same concept, basically.
same concept, yeah.
Yeah. Okay, just checking because I'll just go review that instead of wasting time here.
Okay. Anything else? Okay, so I just don't let me go for more than like 10 minutes here, okay? Because I could very quickly go off the rails here. I wanted to talk to you all about something that's going to be in next class, and that is our number system, okay? Our number system. Has everyone heard that the number system we use is called base 10? Have y'all heard that before? The number system that you've been raised in is base 10. Okay, so some of you are saying yes, some of you are saying no. So let me explain what base 10 is. And I think when I start to explain it, you might actually remember, oh yeah, I did learn this. So when we take a number, let's say we take the number 342, okay? I don't know why that looks weird. Let's take the number 342. And there's usually a decimal place right there, right? We don't write it, but there's a decimal point right there. Okay, so when you're in grade school, you're taught to think about these as if they were in positions, like you have 3 positions there. The first position was how many ones you have. The second position is how many tens you have. And the third position is how many hundreds you have. Does that look more familiar to you now? Yes. And then the next position is 1,000, 10,000, 100,000, million, right? Blah, 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 blah. And then actually, if you go the other way, the decimal points mean something as well, right? Does anyone remember what the digits after, like this tells you how many whats you have, whats and whats? You remember what that first decimal point represents? Like if this was, let's say 5, 6, 1.
Would it be tenths, right?
Tenths, tenths, tenths. This would be hundredths, hundredths. This would be thousandths. Not tens, hundreds, thousands, tenths, hundredths, thousandths, right? Okay. Now, let me ask you another question. If let's say I wanted to add another digit out here to the front of this number right here. What are the possible things I could fill that box with? Someone give me an example of something I could put in that box.
Any real number?
Any real number? What do you mean any real number?
So would
Could
it be?
I put 21 in that box?
Oh no. Okay, so it'd be like a 1-digit number.
A 1-digit number, okay. Can it be, it can't be a fraction, right?
No.
Okay, so what are your choices? What are my choices? I could plug in
1
Whole
through
numbers?
0 through
1. I could plug in 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0, right? Every single position in there can be filled in with one of how many things? So how many possible things are there here? How many options do we have?
10.
10, right? 10. We have 10 digits, right? There are 10 digits that we use in our number system, right? There are only 10 though. All the numbers that you ever have, that you've ever dealt with in your life are going to be using one of those 10 digits, right? One of those 10. There's not 11 options. There's not 7 options. There's 10 options for each digit. Agree with me? Okay. Now, I want to expand on this a little bit more. This right here, another way you can write this number is this. Doesn't this 3 mean I have 3 hundreds? And then the 4 means I have 4 tens. And the 2 means I have 2 ones. Think about it like money, $342. That means I have $300 bills, 4 $10 bills, and 2 $1 bills. Yes? Notice something here, something subtle but important. This could be rewritten as 3 times, now 100 is 10 squared, plus 4, and then 10 I could write as 10 to the first power, plus 2, and then I could rewrite the 1 as 10 to the 0th power, because anything to the 0 power is 1. Now that's weird, but I mean, I could do that. Let me add one more number. Let's say I put a 7 in front of this. This would mean I have what? 7 thousands in front of that, which would be 7 10 to the what powers? Third, right? 10 to the third. So let me try and expand, please. This is going to come together here in a second. What we're saying is that when you write down a number, right? When we write down a number, the first, let's ignore these for now. The first digit in the number is how many 10 to the zeros I have. The second digit in the number is how many 10 to the ones I have. The third digit is how many 10 squareds, and the fourth digit would be how many 10 cubes, and then fifth digit would be how many 10 to the fourths, right? And for each of the numbers that are in front, right, the yellow ones, you said that there are 10 things to choose from. So this is a 2, it could have been a 5, it could have been a 3, it could have been an 8, right? There were 10 things to choose from for each of those yellow things, right? That's why it's base 10, because for each digit, there are 10 things to choose from, and each one of those digits is some power of 10. Let me go backwards here. Let me see if this really makes sense to you. What if I continue this decimal place? All right, I'm focusing on this, this part right here. Wouldn't this be, this 5 is how many? This would mean I have 5 tenths. This would mean I have 6 1/100ths. And this 1 would mean I have 1 1,000th. But I could write that as 5 times, now what is this 1/10 as a power of 10? It's 10 to what power? Negative 1. Negative 1, right? What's 10 to the negative 1? 10 to the negative 1 is the same as 1/10. Property of exponents, you can drop it down. And isn't the 6 step back here 10 to the negative 2, right? 6 times 1/100 is 1/10 squared. Are y'all seeing the pattern here?
It's inverted.
Yeah. So look at these powers. Look at all these powers. 0, 1, 2, 3. So as you go to the left, they go up. And as you go to the right, you just keep subtracting 1. -1, -2, -3. You see that? Nice, clean, from 0 to the left to the right. Everything is a power of 10. Every digit in a number is a power of 10. Is how many powers of 10, you know, how many, for that slot, it depends, depending on what position you're in, it tells you what the power on the 10 is. And then the numbers in front are how many of them you have. And you have 10 options there. That's the base 10 number system, all right? I'm gonna try and expand on this. What about if our system was base 2 instead? What if we had a base 2 system? Well, how many different options would we have? Remember base 10, how many options did we have? We had 10 options, right? So if we're in base 2, how many options would you have? 2 options. What do you think they are? 0 and 1. So if I'm going to write a number down, I have these positions, right? In the first position, I can put one of 2 things, right? I can put a 0 or a 1 there, a 0 or a 1, a 0 or a 1, a 0 or a 1. So those are the only things I can use. I'll put 1, 0, 1, 1, 1. That is what we call a base 2 number. Now think about what each one represents. This means I have 1 something here. This means I have 0 somethings. This means I have 1 something. This means I have 1 something, and this means I have 1 something. But what is it? What are these things that are next to it? Remember, this was 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. So what's next to each of these? Is it 10? What is it? 2, because our system was 2. So this is how many 2 to the zeros I have. This is how many 2 to the 1s I have. This is how many 2 squareds I have. This is how many 2 cubes I have. This is how many 2 to the 4ths I have. These numbers in front are how many of them I have, and I only have two options, none or one. And then each one of these is a power of 2 because we're in base 2, not base 10. What is 2 to the 0, by the way? What is 2 to the 0? 2 raised to the 0 is 1, isn't it? Okay, so if I have, this really means I have 1, 1, so that's a 1. I have plus, now here, I have 0 of these, so I don't have any of those. Plus, okay, what's 2 squared? 4, and I have 1 of those, so I have a 4 here. Plus, okay, 2 cubed is 8, and I have 1 of those. And then here, 2 to the 4th is 16, and I have 1 of those, 16. So let's add these up. 29, this is 29, right? So this means that this number 11101 in base 2 is really the number 29 in base 10, the number system that we work in. So do y'all know where base 2 is used? I'm almost done. Do y'all know where base 2 is used the most?
Would it be computer codes?
Yeah, like coding.
Computers. Why do computers use base 2 as a number system? Does anyone know why computers use base 2? Okay, when it comes to a computer, can y'all see my screen okay? Can y'all see me okay? Okay, when it comes to a computer, electronic devices, you only have 2 states. You either have off, okay, no electrical signal, okay, no electrical pulse, nothing, or you have on. That's all a computer ever understands. That's all a computer ever understands, either yes or no, yes or no, yes or no. That's it, that's all it knows. And that's called binary, 2 different, there's only 2 options. 2 options, 0s and 1s. So your computer only looks as off as 0 and on as 1. So the entire language of a computer can only be those 2 things, those 2 states. So everything in a computer has to be binary. So this number 11101 is the binary representation of the number 29. So when I type in 29 on my computer has no idea what 29 is. It just knows 11101. That's what it knows. So it's a completely different language that the computer speaks in. Now, I promise 1 minute, we're almost done. Wouldn't it be nice? I don't know. I mean, base 10, base 2. You could have any base you want. You could have base 8 where there's only 8 things to choose from and all of these are powers of 8. You could have base 5 where you only have 5 things to choose from and all things are powers of 5. You can have base 16 where there's 16 things to choose from and all of them are powers of 16. There actually is base 16, it's called hexadecimal. You have to use letters because you run out of, you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then you start using letters, A, B, C, D. Okay, it's beyond the scope of this class. My final question to you, I promise, final question. Why do you think that we use base 10? We could have used any base as humans. I mean, you know base 10, that's all you know. That's all you know, right? I mean, that's the one you're most comfortable with, base 10, but I'm trying to explain to you that there's nothing special about base 10. It's just the one that we use. Why do you think we use base 10?
Is it because we use all the numbers in it, like 0 through 9, basically?
Yeah, but if you were raised to believe that the numbers were 0, 1, 2, 3, 4, 5, and that was it, those are the only digits you had, then that would be normal to you, right? That would be normal.
Is it
Why?
because it's the only base that doesn't have to use like letters, like how you said how with the hexadecimal thing, it goes to ABC.
Well, yeah, but if I took out the 8 and 9, you never had ever seen an 8 and a 9, then you would have said, okay, 0 through 7, right? I don't have to use letters, but I could have another symbol over here that you were raised with that you would think is a number. Like I could just draw some weird symbol, right? Like maybe we could have all been raised to believe that that right there is like the number 8. And everyone would think, oh, that's 8 and not have any problems with it. I mean, you know what I'm saying? Like everyone looks at 0 through 9, 0, 1, 2, 3, all through 9 and say, well, those are the only numbers. Well, they're the numbers that we've chosen. Is there any reason why humans would want to just use base 10? What's convenient about it?
It's easier to understand.
No,
No.
it is easier to understand, but why? Why?
Is it because we have like 10
We have 10
fingers?
fingers.
Because we have 10 fingers. That's it. Okay, I promise you, if we had 8 fingers, we would be in base 8. I promise you that's what would happen. Well, we would have bigger problems. We'd have thumbs, we'd have bigger problems. But I'm just saying, like, if we only had 8 fingers, we would be in base 8. If we had 12 fingers, we'd be in base 12. That's what we would know. That would be normal to us. If we only had 1 finger on each hand, we would be in binary. Okay, we would use the same language a computer used because it's convenient. We can count these, 1, 0, 1, 2. We have them right here. That's it, though. That's the only reason. All right. Okay, we're gonna call it a day. We're gonna talk about exponential functions next time. And when you look at an exponential function, exponential functions have something called a base, and that base is a number. And of course, 10 could be the number, 2 could be the number, and there's a bunch of others. E. We'll talk about it next time. All right, that's all I got. Y'all have a good day.
Thank you,
Thank
Professor.
you.
Thank you. You too, Professor.
Hey,
Also, I
sorry,
have a
sorry.
quick question.
Yes.
Sorry.
No, you go ahead, bro. Go ahead.
Thank you. Regarding the homework for tomorrow, we're doing all of the problems that are there,
Yeah,
right?
I did take some out at the end.
Okay.
So you should be
Sounds
able to
good.
handle them all. Okay.
All right. Thank you, sir. You have a good day.
I just want to remind you again. I'll try to log on Wednesday, but I'll be on my cruise. So,
Okay, yeah.
yeah. So if I can't, because we bought the internet for the
Yeah.
for class and stuff. So if it's not strong enough to hold the Zoom, I'll just watch the YouTube videos and try to get the homework in as quick as possible.
Sure. Yeah, no problem. And if you need more time, that's not a big deal.
Alrighty, perfect.
Okay,
Yeah, I'll
have fun.
shoot you
Enjoy yourself.
messages on how it works.
Okay. All right. Have a good time.
So you too. Thank you very much. Have a good one.
Ashley, you have a question?